Okay, so thank you everyone for coming. I know that after lunch people are often a little bit sleepy, especially if you're a carb-heavy vegetarian like me. So what I'm going to do, what I wanted to do today is, let's see. I guess there are three things. First, I wanted to answer some questions that people emailed me about how the operational semantic works in a little bit more detail. Second, I wanted to pontificate about research a bit, and then third, I wanted to get into how we can prove the soundness of the language that we talked about yesterday. So that is, yesterday we talked about a type system for reasoning about or for tracking the imperative programs. And this gave us like sort of a C-like API where we could allocate and deallocate memory, and the type system would ensure that everything happened appropriately, even though we could do crazy things like change the type of our pointers. And what we did was we had our type system, and then we wrote down an operational semantics. And the interesting thing here is that we chose an operational semantics that had no types in it whatsoever. And in fact, it had tons of terms that were actually completely untypable. So let me pause for a moment to bring this down, and I'll show you what it looks like, just to help remember. There it is. So let me bring this down to 300%. Whoops. See this? Still a little bit big. Try that. Okay, close enough. So what we saw was that we had a bunch of type rules. And then what we did was we gave a syntax and operational semantic, a set of terms, and the key additions are that we added to our term language a notation for bare pointers. So, these could be hex numbers if we compiled it down to if we were thinking of this as like a x86 machine. And then for these capabilities, which represented the permission to access memory, we said, well, the value for them is just going to be like this dot right here. There's no real computational content here because it's really bookkeeping that our type system is making us do to enforce that we are going to access memory properly. So there's no computational content associated with it. So it's just going to be like some dummy value. And then we gave an operational semantics which acted on these terms. And part of reduction, let me go down right here, can create and manipulate capability values and locations. And let me pick an example. So in this line right here, what we're doing, there we go, the whole thing fits now. We're saying in the store sigma, if we allocate a new value, then the heap is going to get extended with a freshly allocated pointer, L, and we're going to substitute L for the pointer value, and then we're going to just replace this capability variable C with a token star or asterisk. And so conceptually what happened is we've allocated this region of memory, and we're saying, okay, now that we've done this, we're just going to put in this dummy value for the variable C, which is the capability type. There's no like sort of checking associated with this. It's just a purely static notion, and we're just filling in this star in order to make variable binding work properly. So that's a little bit funny, and someone asked yesterday, I can't see, whether this language satisfies syntactic type safety, and the answer is absolutely not. So you saw earlier last week that one way of proving the safety of a language is we'll say, okay, we'll say that a term has a particular type, and then you prove a progress and a preservation lemma, and then you'll give a reduction relation, E steps to E prime, and then you'll prove progress, which says if E is well typed, in fact in an empty context, then E will step to some E prime, or E is a value. And so that says we'll never get stuck. And then we'll prove preservation, which says, well, if we have a closed term E, and E steps to E prime, then E prime has the type A. Are you able to pick that up? Okay, great. And in fact, actually, it doesn't matter if you can pick that up or not, because this is not what we're doing. And the reason it doesn't work is actually pretty straightforward, because when we do this allocation, we've just created this location L, and there's no typing rule for L's. And then we create this token star for the capability, and there's no typing rule for star either. So it's obviously the case that there's no possible way that preservation could work. So like, a syntactic approach to type safety isn't even going to get off the ground in this case. And you can draw an analogy between this situation and a compiler correctness proof, actually. So you can imagine that in our programming language, with this typed calculus, we have an extremely simple compilation algorithm. So we have two languages, one of which is a typed linear language, whose typing rules you've all seen, and then we compile it into an untyped language that manipulates the store, and we compile it by the identity function. So, or as Ron did, we start with some blue terms, and we compile it by coloring them all red. And what we're going to do is we're going to say, well, how do we know that we haven't screwed up? So the approach to proving type safety will be instead a semantic argument, where we'll say, well, each of these typed terms lives inside of this untyped language, and we can carve out subsets of this untyped language which we know will be well behaved. So we have a mathematical property of safety, and we'll show that every well-typed program is safe, and then is a safe untyped program, and then we'll have a semantic type safety argument. And so that's the approach we're going to take in this class. In fact, we're going to do something a bit stronger, because what we're going to do is we're going to prove more than just safety of the language, which is, if you will pardon me, kind of a boring property. Like safety is just telling us that, okay, you've written a program, it won't crash. Will it compute the right answer? I don't know. It's just not going to crash. So I mean, not dereferencing a null pointer is a thing. It's an important thing. But we write programs in order to actually calculate values, calculate answers, and we'd like to be able to reason about that. And moreover, the other thing we spend a lot of time doing when we're programming is we spend a lot of time refactoring. So you write a program, you say, I don't like this program, and you rewrite it. And you have some argument in mind as to why this program that you wrote is the same as the old program that you wrote, or even that it's a different program, like hopefully a better program. And so what you want to do is you want to have principles for reasoning about programs. And what we're going to do is we're going to see how this untyped semantics justifies a variety of reasoning principles. Let's see, is that the right way to put it? No, I want to change how I say this. So what we're going to do is we're going to tell you how to interpret types, and we're going to say for each type, what does it mean to be a value of this type? What does it mean for one value of this type to be equal to another value of this type? And then we'll use that to decide whether two computations are the same or different. No, I don't want to. Do I want to do this? Let's see. Yeah. Mm-hmm. So what we've got at the end of the day is some programming language in which you can write all sorts of programs, some of which will crash, some of which will behave correctly. And so we'll say we have like some untyped universe U. And this is the universe of programs, or the untyped programs, or the unacceptable programs, or whatever you want U to stand for. And what we're going to do is we want to, like the first idea you might have is you might say, well, you know, this thing here contains all kinds of things. Like it might have numbers like 0, 1, 2 in it. It might have some lambdas. It might have applications. Maybe even it has like, you know, a lambda applied to something in this universe of untyped programs. So we might have lambda x dot 3 in here. And you know, it's untyped. We might even have 3 applied to lambda x dot e. You know, it's got lots of stuff in there. And what we want to do is we want to pick out like particularly well-behaved subsets of it. So that might be the first idea. So let's see. So idea 1, let's say. A type is a subset of U. And so you might say, let's define the natural numbers to be the set, you know, 0, 1, 2, 3, whatever. And that might be fine. In fact, we might even say something like, oh, well, this definition of the natural numbers only includes terms which are literal numbers. Maybe what we can do is we can say something like, a natural number is any expression in U such that you know, E will evaluate down to a numeral. Or I wrote the arrow in the other direction. Maybe even it'll evaluate to a number in some number of steps. So we might say that's what a natural number is. And you know, for the natural numbers, that'll actually work pretty well. And then for functions, let's say if you have two types A and B, and here types, by types I just mean subsets of U, we can say, well, A arrow B, we're going to define as, let's see what we can do. Let's say we'll take them to be all the values such that for every expression in A, V applied to E is in B. So this is just a logical relation, much like the ones you've been seeing that Amal has been talking to you about, much like the ones that you saw in the termination proof for the simply typed lambda calculus, much like the ones that you saw Bob talk about in the computational interpretations of type theory. So we'll say, okay, well, we'll just take a function. Oh, actually, I wrote a v here. Maybe I'll just write f to mean any expression. We're just saying, oh, it's any expression that if you give it an argument of the right type, it'll give you a value of the return of the right return type. And this will be okay. The problem you'll run into with this definition is, well, let me back up. Let me tell you what it does do. And so if all you want to do is establish type safety, then this style of definition will work just fine. So with safety, all we want to do is we want to say that if we have a well-typed program, then it's going to have good behavior. And that's fine. And we could proceed in this style using idea number 1, and it would work fine for establishing safety. However, our ambitions are a little bit stronger than that. So I've been repeatedly saying, oh, yes, we want equations between programs. And so what do I mean by that? So I mean that one of the things that we would like is we'd like to be able to say that one program is equal to or different than another program. So here's an example of an equation that we might want. We might want to say that if you have lambda x, lambda y, and x plus y, we might want to say that this program right here is equal to lambda x, lambda y, dot y plus x at the type. So, this is not a terribly complicated equation. It's just saying that if you x plus y is equal to y plus x, even after you eta expand it. So we're saying addition is commutative, and we'll take it to be the obvious definition of associative. And what we want is to know that we can replace this for this, and no behavior of the program will be different. So we'd like to have these kinds of equations. We might even have more exciting equations. Let me make it super exciting by moving to. We might have like x times y times 0 is equal to the constant function lambda xy dot 0. So if you have this equation, there's lots of things you can do. You can take multiplications out of your program and optimize your program, and that's really fun. If your program runs a little bit faster than it would have otherwise. And so what we want to do is we want to say this program is equal to that program, and if we try to do it using this type of subsets approach, we won't be able to. We can get farther than you'd expect, but ultimately, the notion of equality will end up defining is two expressions are equal if they evaluate to the same value, and these two values are manifestly not the same. So the subset interpretation of types will tell us that we can't establish this equality, and so our principles for reasoning about the equality of expressions are very limited when we have to treat types as subsets. And this is not such an exciting equation, but let me show you some equations which might be a little bit more exciting. So we've been talking about imperative programs, so let's write down some equations about imperative programs. So suppose that we have our program here, and we're going to say if I read from a location E, I have a capability for it, and then I will do an assignment. So I will say, I'm going to take E and assign what I just read from it and then I do a computation. Let's call that t prime, say. So in this program, what we're doing is we have this value, this location e. We dereference it and store the value in x. And then back into e, we assign x. And then we carry on with our computation. So what we've done is we've dereferenced a pointer, written the value we got out back into the pointer, and then continued with our computation. And we really expect this program to be exactly the same as, let's see, like that this second right is redundant. We don't need it. So we expect this to be the same as let xa a for a prime in t. So what this optimization is saying is that this right is completely redundant. And if it happened to be the case that x didn't occur free in t prime, then we wouldn't even need to do the read. So let's see here. So let me put in a side condition here. So if we had the condition that x is not in the free variables of t prime, then we would expect this whole thing to say, well, we've done this read, we've done the redundant write, and then we didn't use the value of that read at all. So we didn't need to have done anything in the first place. So this whole thing is equal to t for a prime in t prime. And so we would have been able to remove both the read and the write from this program. And the point I want to get at here is, let me first pause. So does this kind of reasoning make sense to people? Let me see. Has anyone not done this kind of reasoning in a program they've written? Okay, so that's like total unanimity here. And I want to make an observation, which is that when you're doing this kind of reasoning, what you don't do is you don't say, well, let's assume we have a heap and then reason about the operational behavior of the program. Instead, what we do is we exploit like sort of shallow syntactic facts about the program. So in this example right here, we say, aha, what we've got right here is we've done a read and bound the result to x. And then, because the variable x doesn't occur in t prime, from that we conclude that this program t prime didn't use the result of the read at all. So we're not reasoning about the heap execution. We're just saying here is a relatively shallow condition that ensures this strong semantic property. So, so if we have this rule, let me see if I can. So if we have this kind of rule, there are transformations it doesn't justify. So let's see, what's a good example of, yes. So we might have something like, okay, I'm going to read ED in, and now what I'm going to do is I'm going to say return the value x minus x. We'll call it f of that, because this is a number, along with a. And by the properties of arithmetic, so let's say this is a number, and then by the properties of arithmetic, we'll be able to conclude that, oh yes, x minus x is equal to 0. And then because it's 0, then, oh yes, we no, we didn't need this x, and then we didn't need to do the right read in the first place. So that rule by itself isn't enough to justify eliminating the read. So for deeper properties, or at least properties we haven't proven yet, we don't know that this whole thing is equal to f of 0. So this will hold. This is a true fact that a simple equation like that won't let you justify. But sort of my point is that that's okay. There's a ton of equations that we can get, and if we can get enough of the reasoning properties that we need to prove interesting things about programs, then we're in good shape, because that means that we can reason about our programs by reasoning about the source code that we wrote, and not have to reason about okay, well, if I compile it to this machine and run that code, then this is what will happen. So in some sense, I'm sort of saying the opposite of what Amal was saying in the morning. So I'm saying, well, contextual equivalence is really hard. Is there any way for us to not do it? And so let's think about how not to do it. So what we want is to prove a bunch of equations about programs, and how do we do that? And so what we're really doing here, let me see here, is one thing that's worth noting is that the kind of reasoning I'm doing here only makes sense in a typed context. So here I said, oh yeah, totally x minus x is 0. But is that true? Can anyone think of a counterexample for when x minus x might not be 0? Yes?
Well, if there's no text there, it doesn't know.
Yes, that's right. So, if this were hello minus hello, then, it might crash, or in JavaScript, you might get the empty string, or 0, or whatever. Maybe it's true in JavaScript, I don't know. If you have an empty string, maybe it's 0. But, in a civilized language, this would crash or get stuck. What? Okay, so yes, then this equation is false in JavaScript. So this whole equation only makes sense if we only consider our typed program. So what we really want to do is we want to say this equation holds at the type f of net tensor, whatever our capability type is, capability I nat. So we're saying, well, if we're considering pairs of numbers and capabilities, then two programs at this type, these two programs are equal. And so that's the kind of equation that we wish to be able to establish. And the secret is that, oh yeah, if we're talking about equality as a type, then maybe what we can do is we'll just, instead of defining one notion of program equality, we'll define a whole family of them. So for each type, what we're going to do is we're going to define what it means for two elements of this type to be equal. And so that will lead us to idea number 2. So idea number 2 is types are equivalence relations. Okay, so we'll say, well, we've got this whole universe of stuff U over here, which I'll draw again. And what we'll do is we'll say, well, for each type, let's define an equivalence relation for that type. And we'll use that equivalence relation to decide when two elements are equal or not equal. And so, what we could do is we could set things up so that, at the type nat, we're going to define it as pairs of expressions where they both evaluate to the same number. And we can play the same game for functions. And we'll say a function, let me use x and y, is going to be any pair of expressions where if you give me well-typed expressions, like well-typed arguments, so I'll call this E hat. What I want is for the application to be well-typed, E hat. And so what we're doing is we're saying, all right, great. What we're doing is we're going to define the natural numbers to be those pairs of expressions that evaluate to the same number. We're going to define functions as pairs of expression that if you give them equal results, so we're saying x is an equivalence relation, and we're going to say if E hat is equal to E hat prime, then I want E applied to E hat to be equal to E prime applied to E hat prime. Yes? Okay, yes, that's a perfect observation. And what's your name? Pedro. Pedro said, "Hey, wait a second. Do these relations you're defining, do they satisfy reflexivity?" And I said, "Oh yes, types are equivalence relations on the universe." And Pedro is making the observation that no, they're not. So an equivalence relation on a set U is a relation R such that it satisfies three properties. So the first property is that for every element of U, E comma E is in the relation. So this is the reflexivity property. The second property that it satisfies is in R. The second property it satisfies is symmetry. So it says if we learn that E1 is related to E2, then E2 is related to E1. And the third property that it satisfies is if you have E1 related to E2 and E2 is related to E3, then E1 is connected to E2 and E2 is connected to E3 means that E1 is related to E3. So this is transitivity. And Pedro's observation is, wait a second, reflexivity is not satisfied because in our definition of the natural numbers, we're saying we have two terms are equal if they both evaluate to a number. And not all expressions evaluate to a number. Some of them evaluate to a lambda term. Some of them will crash. Some of them, will do worse things like corrupt memory and expose your computer to hacking. So there's a lot of things in the universe, some of which are good, some of which are bad, and some of which are like awful. And this is a good point. And the way we will solve this problem is by giving up. So a type is a partial equivalence relation. And let me put a big check mark by here. So the Fonz approves of this definition. So what we're doing is, the intuition we have is, for every type, we have like this gigantic, yes?
Can you give me an example of a term that's not in math?
Yes.
But still uses the number?
That's still what?
That still uses the number.
Oh, okay. Well, here what we're doing is we're defining the natural numbers to be the equivalence relation on the universe to be the subset of the universe consisting of those pairs E prime, which relate to it, both reduced to a natural number. So we're just asserting that this is what it means to be a natural number. And so if you have a term that evaluates to a natural number, it's in the relation. It's only reflexive on the subset of U that it reduces to a natural number.
But that's only one.
Yes, that is. So yes, that's right. That's all we want.
So then why is it not reflective?
Because these are partial equivalence relations on the whole universe. So the thing we start out having is this whole universe of untyped terms, and now we're going to identify types by partial equivalence relations on this universe.
I think what you're trying to say is that you can partition into disjoint sets of equivalence relations.
Now, okay, that's a good suggestion. Is that what you meant?
I don't know what I meant. I think it's reflective. For example, two equal functions, they can only belong to the left and then they belong to the right hand function.
Yes. So here's a pair.
They are in the function.
Yeah, that's
And reflective in the domain that you are defining, not in the only one and the use.
Yes. So the mathematical property you're thinking of goes a bit like this. Let me. So if R is a partial equivalence relation on a set U, then what you can define is you can define the domain of R to be the subset of U such that EE is in R. And what will happen is that this relation R is a full equivalence relation on the domain of R. But it's not a full equivalence relation on U. Yes?
Maybe you take a closure of R over U and just say everything else is its own.
Okay, a closure of R on U, what do you mean?
And say everything that's not in R is just by itself reflexive and isolated.
Okay, so you're saying we have a whole bunch of things which are equivalent, and then I'm like at the natural number type, I'm going to say that, like lambda x dot x is related to lambda x dot x, but nothing else.
Yeah.
There is nothing stopping you from doing that mathematically, but it won't have the properties we want. Yes?
the only real thing that stops you from partitioning neatly into disjoint equivalence relation is non-determinism, which if you don't have, it shouldn't be a problem.
Okay, so no, that's not the only problem. So here what's happened is that so here what's happened is that we have defined a semantic type of natural numbers. There's actually nothing stopping us from saying, well, I'm going to define the semantic type prime, which are pairs E prime, where E reduces to some k, and E prime reduces to k, and k is prime. And now prime and the natural numbers are not disjoint.
Yeah, but so you choose your equivalence relations to be the span of your values in the language, right? So if your value is a natural number and a function, then those are the equivalence relations. Try something else, figure out the equivalence relations.
Sorry, could you repeat again?
So your values in the language
Yeah.
are numbers and functions. So
Yeah.
those are the equivalence relations you find.
Oh, okay. So far so in the semantics that we saw yesterday, there's lots more stuff in the language.
Make equivalence relation for every value, union it together, and choose non-determinism.
Oh, okay. So you're okay. So that's an idea which almost works, but it doesn't work. And the reason for this, so this is a bit of a digression, but it's probably worth going into a little bit. So when you have a family of partial equivalence relations, the partial equivalence relations form a lattice, and so in fact they form a complete lattice. And the way it works is that you'll say if R and S are pairs, then you can define a meet operation on this lattice, and you can say, okay, I'm going to find the least upper bound, the greatest lower bound of R and when I don't know. So this will be yeah, it'll be the infimum of the set, and it's just going to be the intersection. And the trouble is that, like, the intuition you have is that you can say, oh, I can define a supremum.
You don't have the axiom of choice. So
It doesn't have to do with the axiom of choice. Like, all of these are just ordinary numeric terms. So the problem is that your intuition is, oh, R join S will be the union, but that's not true. And it's not true because what you have to do is you take the union, and if R and S overlap at all, you might have to add a whole bunch more elements in order to make the relation transitive. So it's the smallest transitive relation containing R union S. And that transitive closure that you take sort of breaks your idea. But this is all a bit of a digression, but it's still good to know because for type system features that I'm not going to talk about in this lecture series, those properties are very important. Yes.
I'm curious how you would define a type like the natural number if your evaluation wasn't deterministic.
If your evaluation wasn't deterministic.
Suppose it flips a coin and returns 5 sometimes and false other times.
Okay. Yes. So, okay. So, yes, that's true. But if you have this coin flip operation, it's not confluent. And yes. So what will happen there is, and actually, for the kinds of languages that Ron and Damal are talking about, like this possibility of like an effect happening and breaking confluence is actually a serious problem. And so this is why what Amal did was she said, I'm going to define a value relation. So I'm going to say the values of natural number type are going to be exactly the natural numbers. And then what she did was she then defined an expression relation, and this expression relation was permitted to have effects. And so she'd say an expression of natural number type, I guess her language was still deterministic. So let me do what she did first, and then I'll tell you a little bit about how you have to handle non-determinism. Okay, so the idea is you'll say, okay, well, natural numbers, the natural number relation are those pairs of are just, n is related to n for all n. The values. And two expressions are the same. So let's say E is related to E prime. And in fact, let's even put in a store. We'll say, no, let's not do that. E prime is related at the expression type. And now the thing you have to do is you have to decide what the equality is. So what you might do is you might do something like, say, let me do the, you might say, okay, for all n, if there is a reduction sequence so that E reduces in in some number of steps to n, then E prime reduces in some other number of steps to n. And if E prime can reduce to n, then E can reduce to n as well. And so what you do in this case is you'll say E and E prime are considered to be the same computation if any value that E can get to, E prime can get to, and any value that E prime can get to, E can also get to. So they can simulate all of their behaviors. And so you'll see that there's actually a sharp distinction between values of natural number type and expressions of natural number type. And the way this will cash out in a syntactic type system is that, well, in two ways. First, you can either have different typing rules for values and expressions, or you can have introduce a monadic typing discipline, where you say, I have expressions which are those deterministic terms which reduce to a value deterministically, and terms of monadic type are the ones that can perform this kind of effect. And the tricky thing about effects in general is that you do have to ensure that you have an equivalence relation on them so that you can prove the monad equations. So did that answer your question or more?
I think so, but that definition of expression type holds if any execution trace has been both reducing to the same. But there are also some execution traces where they might evaluate different numbers.
Yes, that's right. So this is saying, so right now we're saying we've got E and E prime, and we're saying anything that E can do, E prime can do. And furthermore, anything that E prime can do, E can do. And so that's sort of the definition. And you might also want to say furthermore, oh yes, there exists some n such that it, and you might want to say that that these expressions only evaluate to numbers, for instance. So you don't want it to have like 5 or string, or 5 or hello world. So you might want to say, well, okay, for all values, if E reduces to a value, then V is a number. And likewise for. So So non-determinism is a tricky case because it actually turns out to be a very challenging effect to handle. And in this case, it's not so bad because we're sort of imposing the restriction that everything is terminating. But if you combine non-termination and non-determinism, like the mathematics gets very, very, very challenging. So if you're interested in that, like I would recommend, well, actually, I would recommend not being interested in it. But but if you decide to ignore my advice, then you should look up the work on power domains. What? Power domains. So if everything is so if everything is terminating, then you can sort of the intuition is you can interpret an expression of non-deterministic type as a set. But if things are not terminating, then it gets very subtle because you have to consider, okay, you have to distinguish different forms of possible non-termination. Actually, it's like really there's a word in civil engineering or urban planning called an attractive nuisance, which is something that's a hazard but attracts people to it. Or like if you have a pool in a neighborhood and there are in which small children live, like your building codes will often say you have to fence it off because small children love water and small children also frequently don't know how to swim. So that's an attractive nuisance. And power domains are an attractive nuisance because they're full of absolutely beautiful mathematics that can devour people whole. So like it's full of all sorts of connections to like, topology and lattice theory and like, lots of deep and wonderful mathematics. But because of that, it can consume arbitrary amounts of time. Okay, so what we are going to do is we're going to define types as partial equivalence relations. And we'll have, because we have two families of types, the intuitionistic types and the linear types, we're also going to have a lot of cases in our logical relation. So this is the moment at which I am like extremely jealous of Amal because she just had numbers and functions in her language, and so defining a logical relation isn't that bad. Unfortunately, we've got more types than that. So. Okay. Okay. So, is this visible on the screen or is it too small? Okay. Yeah. So initially, what I want to do is I want you to like zoom in. I guess you can see the bit that I want you to zoom in on. So that's fine. Okay. So initially, defining the logical relation for the intuitionistic part of the language isn't particularly difficult. And so what we're just going to do is we're going to initially define our logical relation on a bunch of value relations, and then we'll take the closure with an expression relation as well. So the values of type unit are just units. So we'll say at unit type, unit equals unit. So I hope that is an intuitive definition. There is a less intuitive definition of unit, which I'm wondering if anyone can think of. What? Ah, okay, you got it. That was faster than I expected. So Jeff suggested, well, at unit type, maybe we can relate all values. So let's see how quickly I can compile LaTeX. One. So v. Okay. So the suggestion was we could have chosen VV prime for all values. V prime in math RM. Okay. So this is kind of so live coding LaTeX, I think I can anti-recommend. So Jeff's suggestion was an alternative definition for the unit type is we could just define it to be all values. So every value is related to every other value at the unit type. And this is actually a perfectly fine definition. And the reason for it is that in our type system, we don't have any ways to eliminate a unit. So there's an introduction rule for units, and then there's no other rules referring to them. So that means that there will be no well-typed program which will ever look at a value of unit type. So there's no way to analyze it, analyze a unit value. So therefore, semantically, we're totally justified in saying, well, the unit type is any value, and we're going to equate it to any other value, and that's safe because we'll just never actually look at it. And if Amal were here, she could tell you things about compiler correctness because this kind of reasoning is often used in compilers to say, well, I have a type that I can't look at, so that means that I don't need to initialize its memory, and so this will let me execute this loop a few nanoseconds faster, and this is fantastic. And then for the product type, however, we do have ways to look at products. And we'll say that a product x times y is just any value whose first projection is in x and whose second projection is in y. And again, we're defining this as an equivalence relation. We're saying v is equal to v prime if first of v is equal to first of v prime at x, and second of v is equal to second of v prime at y. So there's not much surprise. There's not a big surprise here. And similarly, for the arrow type, we're saying v is equal to v prime at a function type if given two expressions which are equal at x. So if e equals e prime at x, then we want v of e to equal v prime of e prime at the y type. And the pointer type, okay, yes, and now I can explain this little row here. So what we saw yesterday was that when we introduced the typing rules for pointers, we introduced an extra context to name all the pointers. So our judgments all grew this extra sigma. So we had gamma tells us with in location context sigma that this term E has the type pointer of I, and the idea was I had to be a name that was bound in sigma. So when we interpret a type, we actually have to give an interpretation to all of those variables. And so what rho does is it'll take a sigma and send each element of sigma to a location. And so the pointer type says that the type pointer x is a singleton type where row of x, which contains the one element row of x. So we look up a location in row, and then we're saying that's the meaning of the pointer type. So yes.
You characterize pairs and functions by their eliminations here.
Yes.
Is that essential to what you're going to do later, or is this kind of arbitrary?
Okay, so the question was, right here we've defined functions by an elimination. And what that means is, here I didn't say that x arrow y had to relate to lambda terms. I just said, give me any two values, v and v prime, and if their application is well typed, then I'm happy to call that a function. Let's see. If the alternative is okay. It is so a friend of mine once who works on decision procedures was listening to me talk to a collaborator once, and she said, you know, I'm really glad that I'm not a type theorist, because when I have a problem, I can just do a proof and solve it. But like with you type theorists, like it's not enough to solve the problem. You have to solve it the right way, or it doesn't count. It's like religion. And part of my religion is that functions are defined by their elimination. And so I do not like writing lambda x e comma lambda x dot e prime, because, you know, a function is defined by, you know, its extensional behavior. And so I don't want to say that it has to be a particular piece of syntax. Yes?
But you've also done so for the pairs, which is more much
Yes, so I've done that for the pairs. And that is because in intuitionistic logic, there are two legitimate ways of thinking about pairs. You can think of them as being defined by first and second, or you can think of them as being being defined by their value introduction, which is the tuple. And so you have a choice, and I chose first and second because it has a nice analogy with unit, where you can think of x times y as saying, okay, I have a binary product, so the two projections have to work. And then for the unit, you can think of it as a zero-ary product. So it's a pair of values where none of the projections have to exist. So because of that parallelism, I chose first and second. Later on, for tensor product, I will do this with a value pair. And there you don't have a choice. There's only one way to do it. So on a less religious note, the other reason to use this define functions by elimination is if you want to type constructors as at function type. So if you want to view successor as a function of type nat arrow nat, then you'll want this kind of semantic definition. So for instance, this is small. Let me make it bigger. Okay. So if, as all right-thinking people, we define the natural number type, we'll see that 0 is a perfectly good value of natural number type. And if we just try to write successor, OCaml will whine at us. And it'll say, no, this is a constructor. It is not a function. This constructor takes one argument, and you didn't give me anything. And so instead, you have to write like that. And in order to get a function, you have to do the eta expansion and say lambda x s of x to get a function type. Haskell makes the opposite choice. So for reasons of religion, OCaml's choice is better, but for reasons of programming, Haskell's choice is much, much better. So similarly, we have the G type, and here something interesting happens. So we'll say that G of t is equal to G of t prime when t t is equal to t prime at the linear type A. And there's a whole bunch of extra syntax here where I say that what I'm doing is I'm saying this is a term in a particular machine configuration. So I'm saying that the interpretation of a linear type is not just a pair of terms. In fact, what we're going to do is we defined intuitionistic types as partial equivalence relations on expressions. And we're going to define linear values differently. What we're going to do is we're going to say a linear type is a per on machine configurations. That's an extra paren. And recall that a machine configuration is a pair sigma t, where this is a store, and this is a linear term. So what we're doing is we're saying, well, we're using linear types to talk about ownership of memory. And so for instance, if we have our capability type, then what we're really doing is we're saying, well, this t is some dummy value. The important thing is that it owns the pointer location, the chunk of memory where I points to a value of type x. And how can we keep track of what memory a linear type owns? And well, if we need to keep track of what memory it owns, let's keep track of what memory it owns. So it's a partial equivalence relation on whole configurations where sigma is the memory that this program owns, and t is its value. And so what we've got is instead of having our equivalence, our semantic equivalence being defined on terms, we're defining it on pairs of terms and the memory they own. And let's see what this. Okay. Okay, that's almost enough space. Yes? What is the type of row? It sends a variable to a location. So locations are the addresses, which are denoted by L. And row will send the variables in sigma to locations. So that's why I wrote row of x. So it looks up the location corresponding to that variable. Okay, so now to get to David's question, the first two lines are the unit and the tensor product in linear types. And here, instead of asserting, oh, it's any pair of values, what I'm doing is I'm saying the unit type are precisely the units. So unit here is equal to unit, and that's it. And the reason for that is that we have an elimination form for the unit type in for the unit linear type, which is a pattern matching elimination. So what we're doing is we have a rule that says, oh, if you see let unit equals unit in T, this thing should be equal to just T. And in our operational semantics, if this is not a value which is not unit, we get stuck. And so that's why, rather than saying it's any pair of values because we never look at it, we say, well, we do look at it in the linear case, and because we can pattern match on the unit, we have to make sure that they're actually units. And similarly for pairs, a value of A tensor B is a pair of values, UA and UB, and U prime A and UB prime. And I apologize for the profusion of parentheses. I've gotten used to it, so I didn't realize quite how bad it was. And furthermore, A tensor B owns some memory. So remember that every value of linear, the semantic linear type relates configurations, which are the memory, a value, and the memory it owns. So we're saying that when you have a tensor product, the memory that it owns can be divided into two parts. So if you have a pair UA, UB, then the memory it owns can be divided into two disjoint parts, sigma A and sigma B. And similarly, the memory that the second pair owns can be divided into two parts, sigma prime A and sigma B prime. And now what we'll do is we'll say, now that we've divided this up, we can say that sigma A UA is related to sigma prime A U prime A at the type A. And likewise for B. So does that make sense? Like if you have any questions at all, please ask me now, because this is actually like sort of the key thing that makes everything work. And if you have even a slight hesitation, feel free to ask, because like understanding this is like 90% of understanding the semantic interpretation of linear types. Yes?
So what is the reason that we can eliminate the unit in the linear fragments but not in the intuitionistic fragments?
So in the intuitionistic case, both choices work, and so we could have defined pairs in this style in the intuitionistic fragment, so sort of with pattern matching style, and that's equivalent to defining it with projections. In a linear type system, projections and pattern matching are not equivalent. So it's a case of, so whenever you have a more restrictive type system, like linear logic versus intuitionistic logic, the more restrictive system can make distinctions that the less restrictive system can't. And so in linear types, you end up with two product types. So you've seen A tensor B. And what I didn't tell you about is that there's also a second pair type in linear types called with. So A with B. And this one has projective eliminations, and this one has pattern matching eliminations, and the two types are not equivalent to each other. And the sort of the critical thing about the tensor product, A tensor B, so this one right here, is that a value owns some memory, and with a tensor product, we're saying that the memory that a value owns can be divided into two disjoint parts. There's the memory that A owns, and there's the memory that B owns, and these are known to be different. So when you look at the capability type, I'm going to skip over functions because I think looking at capabilities will illuminate things a bit better. What's going to happen is that we're going to say that a value of capability type is just a unit, but it's a unit where the memory it owns is sort of the one element heap, where L points to V and L points to V prime, and L is equal to rho of X, and V prime are related at X. So a capability is telling you, I own this one element chunk of memory holding this value V. And so what that means is that if you have a value of so if you have the type capability IX tensor capability JY, then what you have is you have information about two disjoint pieces of memory. So a value of this type is going to own a piece of memory which can be divided into the I piece of memory and the J piece of memory, and these are separate. So so linearity is enforcing the disjoint ownership condition. And this is how linearity enforces a disjoint ownership condition, by saying, well, the meaning of a pair is that these two components each own a disjoint resource. And that means that that means that if you have a value of this pair type, you actually have two resources: the resources associated with A and the resources associated B, and no one else owns them, and you know that those two resources are separate. So you know you have two separate resources. And this this also drives the definition of the function type. So what the function type says, I'm going to make it go down so that I can point to it. So the function type right here, it's long, but it mimics the function rule from the intuitionistic case, where it says that if I have an element of A, then I can apply, like if I have two values U and U prime, and I have two expressions TA and T prime of A, then U applied to TA and U prime applied to T prime are in B. And that's the same as in the intuitionistic case. Yes?
Just checking, should the L relation be index by row?
Yes, they should be. So, sorry, I need to see your name tag. Okay, so what Dustin said was, oh, look, you forgot to put a row right here. And yes, I did forget to put it there. And so I have to stop soon. Oh, dear. So what happens is that, if you take related arguments and do an application, then you get related results. And the that part looks exactly the same as in the intuitionistic case. The part that's different has to do with the resources. And because we're in a linear setting, this function U owns some resources sigma. And what we're going to require is that the resources associated with the argument, sigma A, has to be disjoint from the resources associated with the function. So you can only call a function if you pass it an argument which has a disjoint set of resources. And this means that if you have a function and you are passed as an argument a capability, now you know that this resource that you got is disjoint from all of the resources you own, and furthermore, now you have unique ownership of this capability. So you can use it as you like. And that's really like this resource management stuff is really how linear types differ from ordinary intuitionistic types. Well, yes. So I will say that decisively, despite the fact that there are other interpretations of linear types. This is one of them, and it's a very useful intuition. Okay, and I don't have that much time, so what I will talk about is the interpretation of computations. And this computation type is really where all of the imperative actions happen. So in the linear part of the language, all we were really doing was bookkeeping of resources. So tensor products let us put together disjoint resources. Functions let us say, well, if you give me some separate A, I'll be able to produce a B for you. And capability is just said, here's a piece of memory. And if you want to read or write from it, then you have to do it in this monad. And almost the idea is that two values are in the computation type if there is some execution from sigma u to sigma 2 u2 such that sigma 2 u2 is in the value relation. So it's saying I have a computation. If you perform the computation, then the heap will change from sigma 1 to sigma 2. And likewise, the thing that it's equal to will change from, where is this? Sigma 1 prime to sigma 2 prime. And then the resulting values, u2 and u2 prime will be in A. So it's saying, okay, this computation is at the type A if it can perform some changes to the heap that will leave you in an A state. So it lets you change things. And I said almost because there's one additional thing you have to do. And you have to say, well, we also have to require that if there's extra stuff, we ignore it. So we say that these two configurations are related only if for any frame f, so frame phi, you can stick it on and evaluation doesn't touch it. So what this is saying is this is a way of enforcing the property that you do not modify any resources you do not own. So we're saying for any possible resource you don't own, it's going to be left untouched by your evaluation. And the reason that it's necessary is your correctness proof will fail without that condition. Let's see, right here. So when you try to validate this rule right here, you'll fail. If you don't have this extra phi condition. And what's going on is we're saying, well, I want to evaluate t first and then continue evaluating t prime. And t prime can refer to those other values in delta prime. And so in order for this typing rule to be sound, we need to know that evaluating t will not perform any modifications which change delta prime. So if you've done monadic programming in Haskell, you may have heard people talk about monads in Haskell being strong. And that means that if you have a value A and a computation B, you can push it into the monad. You can say, oh yes, I can send, I have this A and I can treat, and a computation of type B, we can treat it as a computation of A times B. What this extra phi thing is doing is it's ensuring that the monad we're defining is strong in the sense of, in the same sense that like Haskell definable monads are strong. Separate, yes, did you have a question?
Yes, I did. Can you go back, I'm sorry, I feel like I interrupted you, but can you go back to the logical relation for T-A?
Yes.
Can you explain why you restrict the terms u sub 1 and u sub 1 prime doing computations that eventually step to a value?
Yes. So one of the things that we're enforcing is that all the programs in this language are total. So everything halts. So we don't, so when you have a state in a programming language, you can you can implement non-termination even without like explicit recursion. So you can implement recursion with state in ML or Haskell or Java. And basically the way you do this is you can implement recursion by sort of a backpatching update. So you create a pointer pointing to some dummy value. You pass a function dereferencing that pointer to the thing you want to take a fixed point of, and then you update the pointer with the result. And now you've made a loop through the heap. And this is exactly the way linkers implement recursion. And so one of the features of linear types is that you can say, well, we still have state, we even have higher order state, but things are crafted so that it's no longer possible to implement unbounded recursion. So it's a way, well, it's a way of showing that, like, you know, the limitless power of higher order state has been tamed.
Actually, why do we need that property then?
What?
We only need non-termination because you want to multi-step to something in the end. I'm being really vague here.
Okay, so let me break this up a little bit, and I'll need to stop in a minute, but I can answer your question at least, I think. State in general is an extremely powerful effect. So you can implement, so in ML or Java, you can implement fixed points using state. Let me see if I can maybe even, this is going to be a risk, but and we'll say F has the type A to B to A to B equals, and now we'll say, let's create a pointer okay, and now we'll say let G be F of fun A goes to bang R of A in R gets assigned to G, and now we'll return G. And let's see if this whole thing type checks. Yes, it does type check, so I think I got it right. And what we've just defined is a call by value fixed point operator. So I'll call this factor equals fun fact n goes to 1 else fact of n minus 1. And let's try fix factor. Okay, and now the moment of truth. Oh, okay. Oh, I forgot to, I defined this wrong. Okay, so yes, there you go. So, what? This is kind of a, so this program is called Landon's knot because Peter Landon discovered it in the 1960s. And I think some ALGOL compilers might have used it to implement recursion. And so it's long been an example of why the semantics of state are so hard. Because you can have a language that doesn't have any fixed point operators in it, and then the moment you add references, suddenly the language has full non-termination in it. And so you have a collection of features that individually look like they don't add up to recursion, but then, like for instance, the type of ref is A to A ref, and the type of assignments is just A ref gives you, and an A will let you do the update, and then the type of dereferencing is just give me a pointer and I'll give you an A. And you'll notice the absence of higher order functions in any of these signatures. And it's actually it came as quite kind of a shock to a lot of people to realize that, adding innocuous looking primitives like this were enough to make a language Turing complete. As many of you know, like the moment you have things like non-termination in your programming language, the semantics get much more challenging. And so This was quite a shock, and it kept a lot of people understanding the semantics of state, kept a lot of people employed for many years, and has continued to do so. And so it was actually a really clever discovery by Amal and Matthew Flewitt and Greg Morissette that you could have, proper state pointing at anything, and if you give it a linear type discipline, you haven't broken the normalization properties. So in the logical relation here, we're saying that a value is in this computation type only if it terminates. And we'll still be able to show the fundamental lemma for the type system before using the semantics. And that proves that every program you can write in this language terminates. And so, sort of one of the benefits of this approach is that it lets you decompose state into smaller pieces. So like you don't have to like take a big gulp and understand the semantics of like a fully Turing complete language at the same time that you're trying to understand state. And so, this is kind of a powerful and useful discovery. And it also means that when you work in a type discipline like this, it makes it much easier to establish the total correctness of your programs. So if you have a linearly typed program that manipulates state, you know without having to do a proof that this program is going to terminate. And so you don't have to do a termination proof in addition to like a functional correctness proof. So this is good for like a wide variety of reasons. And since I am out of time now, I will just tell you the thing that is necessary to do. And so just as Amal did, once we have this logical relation, what we can do is we can extend. So this relation is defined on closed terms and closed machine configurations, and we want to lift it up to talk about open terms. And once we do that, we can prove the basic lemma, and with the basic lemma, we will be able to prove the good properties of the language, including the equations that I started talking to you about at the very beginning. And I want to recommend one paper to you, which is Sam Staton's Completeness for Algebraic Theories of Local State. Sam is he's an extremely nice person, but he's also like one of these terrifying super geniuses. And so there's a lot of very advanced math in this paper, and the purpose of all that advanced math is to prove that there is a set of, I think, 14 equations that characterize reasoning about local state. So if you can prove these equations, GS through G7, B1 through B3, and LS1 through LS4, then any equational property about local state that actually holds, you'll be able to prove with an asterisk. And so, this is the kind of equational theory that we want for our programming language, because it lets us talk about what it means for two programs to be equal without having to break out the logical relation and reason directly in the model. Like we can reason at a syntactic level and use the model construction once. Okay, thank you.